Good afternoon and welcome to today's webinar from XP Solutions called Direct Rainfall. My name is Gavin Fields and I'm a Senior Water Resources Engineer here at XP Solutions. As you're aware, the topic of today's session is on direct rainfall, and I have with me Dr. Bill Syme from WBMT. Today's webinar is part of our XP Live webinar program. There are several pre-recorded webinars available via our website. Two previous ones to this on our 2D modelling series. This is our third webinar. However, I will note that this particular webinar can be viewed completely independent of the previous two. It's not as much as it's a series, it's not a follow-on series. And today we're trialling a new format to see how this works, where hopefully you can see both our PowerPoint slides show our interface plus myself and Bill live on the screen, considering the two of us are talking together. So we'll try this today, and if this is successful, we might continue to do this into the future. Again, we've got Dr. Bill Syme here with me, and Bill will be presenting the first part of the session as we get through. The purpose for today's session is to talk about this, what is relatively new. It's been around for a number of years now, I suppose, but it's certainly maturing as a hydrologic method, is direct rainfall. And so Bill will run through a bit of the introduction of what direct rainfall is, a bit of theory and application, and I'll come in and towards the back end with some of the application in our software and a bit of a demonstration on a couple of case study sites that we've got some models that have been made available to us. For those who aren't aware, our product XP Syme and XP Storm both have the 2D module within them where direct rainfall can be applied if you have that XP 2D module. The software obviously has enhancements to both sanitary applications, river modelling applications, good links with GIS and other third-party applications. So I'll pass over to Bill at this point, and hope you enjoy the session.
Thank you, Gavin, and hello to everyone. So direct rainfall, well, it has been around for, I guess the first time we ever applied it was in the mid-2000s, but it's only been in recent years that it's really been applied to a much greater extent. And effectively what's happening is the rainfall is just being pushed straight onto the 2D cells. There's no flow boundaries as you would traditionally know them. And it effectively replaces the need to have a hydrologic model or unit hydrographs or some other more traditional way of putting the water onto your model. One of the reasons it's becoming very popular is that it's very, very easy to set up. And that's got its pros and cons, of course. And probably the biggest risk to all of us who are using direct rainfall is that it is new to the industry. And it's, as we'll talk about during this webinar, it's very, very important, like all modelling, I guess, but when you have a new approach, you really do need to look at your results, question them, compare them with other methods, and so forth. So direct rainfall is, I think, very much with us, and into the future it will be used more and more and more. And I don't know whether I'm brave enough to say it will replace hydrologic modelling, but it's certainly, that's how some are treating it. So let's have a look at what happens. So how does it work? Runoff is basically the rain just goes directly onto your grid, on your 2D cells. And clearly the area of your cells has a bearing on things. The finer the cells, the finer your representation of the topography and so forth. That's not to say you need to go down to ridiculously small cells to have a good model, nor do your run times get very long with those very small cells. But your cell area has to be commensurate with the hydrologic processes that you're trying to replicate. Rainfall depth, once again, pretty clear on that one. The more rain you put on, the more you're going to have runoff. And there's nothing really new there in terms of an input mechanism. It's just a normal rainfall hydrograph will just be put onto those cells. The engine is now capable of handling variations in rainfall grids spatially and temporally, and that's a feature that the XP guys are looking at putting in. The cell roughness is something we'll talk about more in this webinar, but it's very, very important. And as you can imagine, if you're having rain onto a heavily vegetated grassland, literally your cell might only be a few millimeters deep, and how the water moves between those cells is very dependent on how you decide to specify the roughness of those cells. And the slope between cells has another bearing on things. Now, I'm not saying you should be modelling the sort of terrain that's in that photo there, but yeah, I mean, we are seeing applications, particularly with the GPU solver that will handle that sort of terrain and give you some pretty amazing results. But once again, you have to be very careful where you're applying this. And as we'll discuss, direct rainfall is very much suited or aimed at the flattish urban areas where it's very hard to delineate your hydrologic catchment boundaries. And a very big part of direct rainfall, depending on where you are and the type of soils and the intensity of your rainfall, is your rainfall losses and infiltration. These parameters can actually have the biggest bearing of all on what sort of results you come up with. It does depend, like the east coast of Australia is not quite so critical for your 100-year event where you have very large rainfalls and small losses. But we've recently done a study in Christchurch where, and this is based on a real flood, where somewhere around half to three-quarters of the rain for about a 50-year event was basically infiltrated into the ground. So your infiltration can be a very important parameter. So what happens is that the water feeds onto the cells. It can flow in the four directions that are offered. The storage of the cell that's pretty straightforward, it's just the area of the cell. What is actually happening is that the full 2D equations are being applied no matter where you are within your model. Now, if your model cell is literally only a few millimeters deep, the dominant term in your equations will be the friction term, which is the Manning's equation usually. And on sort of steep terrain, it will be very much pretty or entirely dominated by that equation. So how you represent Manning's and roughness for those very small cells is very, very important. As the water gets deeper, or as you approach the more your rivers and floodplains, as water comes down into those areas or into your drains, the full 2D equations are still being applied, and you'll see the other terms such as inertia and eddy viscosity and so forth have a greater influence. But what's quite nice with this system is that the full 2D equations are being applied everywhere, and so there's a seamless transition, if you like, from that sort of very shallow runoff, friction-dominated flow through to your deeper flows where your other terms can become quite important. So where would you use direct rainfall? Well, I guess we're seeing it used everywhere, really, but one of the most common areas is the very flat terrain catchments, because the primary problem with the more traditional methods in these areas is that it's very, very hard to delineate your subcatchments. So if you have to create a vast model or raw model or whatever model, you have to delineate subcatchments, and that can be very, very awkward in these very, very flat terrains, particularly well suited to the urban areas. If you have, sometimes you do have catchments which interlink. The example I mentioned in Christchurch, there's cross flows between catchments. It's very flat country. Once again, it can be very hard to delineate that in your hydrologic modelling. And with this approach, it just happens automatically. If you're in an urban area, you have to, there's a pipe network underneath, and it's flat terrain. Once again, that's a really, really good area of use for this type of approach, and certainly has been used extensively in urban areas of Sydney and elsewhere. As I said earlier, it's very easy to set up. So in many respects, it simplifies the whole modelling process substantially. You don't have to delineate your subcatchments. You just basically put rainfall onto your model. If it's a small catchment, a small urban catchment, your rainfall is typically it doesn't vary spatially. And so you literally have one rainfall pattern varying over time. You put it on your model and away you go. It's not simplifying the calculations. You're actually going up quite a large step in terms of your computational effort, and you are also increasing the resolution of your delineation of your land use and topography. Everything is delineated down to the 2D cell resolution, whereas a hydrologic model, of course, has these lumped subcatchments, and this doesn't have anywhere near the fine-scale resolution that you have in one of these models with respect to topography, soil types, land use, and so forth. So while it may be easier to set up these models, you are creating a model with a lot more sophistication. So what are the advantages and disadvantages? Well, the advantages. So as I've mentioned, there's no need for a separate hydrologic model. basically just comes out. So you don't have to spend time developing one of those models. It reduces your work setup time, improves your workflow efficiency quite substantially, and so forth. The assumptions on the catchment outlet are not required. It depends. If you have a very flat exit from your model, you don't have to worry too much about how the water is coming off your model. So there's some simplification there. You don't have to delineate your catchments, as I've mentioned. That makes life a lot easier, and the cross-catchment flow is just going to happen automatically. One nice thing, of course, is your overland flow paths will be shown, and you can see those very, very clearly, which can be very, very useful when you're doing some broad-scale mapping of where your problem areas might be. The disadvantage is it is a new technique, as I've said, so it's really important to recognise that. You do need to scrutinise your model heavily, particularly when you're doing your first direct rainfall models. That really applies to all types of modelling, but this is new to the industry, and it's very, very important. If you like, always question your results. That's one of my mantras, I guess. You should always question your results. And so you do need to look closely at your model results, try and calibrate your model if at all possible, and so forth. Big downside to a lot of people will be the run times. So you are going from hydrologic modelling, which is very, very fast. Even if you're doing hydrologic modelling onto a 2D model, your number of wet soils will be a lot more using the direct rainfall approach, because effectively with direct rainfall, pretty well every cell within your catchment is often wet, and so the number of wet cells in your model increases enormously, and that can obviously reduce your run times. If you're just comparing it, if you're just doing a direct comparison with hydrologic modelling, hydrologic models, of course, are very, very fast these days. You do need good digital terrain information. That's a lot less of an issue these days than what it used to be, but you do need to have a good DEM. You don't have access to that sort of data, or the data is very poor or coarse, you may not achieve the sort of outcomes that you would like. If you're defining very small flow paths and your resolution is too coarse, that of course will not solve your problem, but then neither would hydrologic modelling. So if you are trying to get down to very, very small cell sizes to pick up those very small flow paths and your model's becoming too large and too unworkable, well, you may have to rethink your approach. Once again, coming back to the very shallow flow, you do need to think that through with your Manning's N roughness range, and we'll talk about that a bit more. Another thing to just bear in mind is that if infiltration is an important parameter, if there is a lot of infiltration in your catchment, you will need to have, normally have to have some good soils data that you can feed into the model, and so you need that type of data as well. So, model setup. What are the things we need to go through? Roughness is an important part of the process, as I mentioned, your losses of infiltration and your grid cell size. So model roughness. There's nothing wrong just when you're setting these models up with just applying a constant roughness just to see what happens when you apply that rainfall. Is something I keep telling all my modelers is that just always keep those computer runs going, because you need to get a feel as to what's happening in your model. So you can very quickly set these models up in a very, very short time and get it running. Even if it takes all night to run, you can set them up in 15 minutes. So once you've got the data, just get something running, get a feel for where the water's going, and get a feel for what's going to happen when you make your model a bit more detailed. But in reality, you may need to look, particularly if you're calibrating the model or you're benchmarking to some other means, you may need to look at using depth varying roughness. And that there's a few schools of thoughts on this one. Certainly for grass or long grass, where when the water is only a few millimetres or centimetre deep, you would typically have a high roughness for those very, very shallow depths, and fairly quickly transition to a normal conventional Manning's N value as the water level gets deeper. The rainfall loss model. Now, there's two ways you can, if you like, lose rainfall. You can apply your conventional initial continuing loss to your rainfall. So this will take those losses off the rainfall. This is not infiltration into the ground. So if you apply an initial loss, continuing loss to your rainfall, that comes off the rainfall before it actually is applied to your 2D cells. So nothing new there. And if you're using an infiltration model, fairly unusual to be also applying initial continuing losses. So one time you might apply a small initial loss is for some sort of interception loss due to water on trees, possibly on the ground, some sort of slight ponding effect. But if you are using infiltration, normally you would have these initial continuing losses set to 0. Really the way that things are going is we're increasingly using an infiltration method. So what's happening here is the water is only being lost from the model if where the cells are actually wet, where you actually have water in the model. So even after the rain is finished, you can continue to have infiltration into the ground using one of these methods. Now you basically specify different soil types, and the different soils you can have different methods. So you can have one soil using green ant, another soil using initial continuing loss, another soil using Horton. So you can mix them up and as you want to. If you're using the green ant method, there are the US standard soil types are directly built into the two-flow code, so you can actually just specify sandy, loam, silty clay, whatever the classification is, and that will automatically set the green ant parameters. You can, of course, set those up yourself if you wanted to. There's also the initial continuing loss approach used as an infiltration mechanism. So it's the same principle as the rainfall excess. So effectively you can lose so much water to start with and then you lose it at a constant rate. There's also the Horton method, which is built into the engine and will be out with the XP's 2015 SP1 release. So that effectively allows the continuing loss to decrease with time. So you have all these methods and all these options, and once again, when you're new to it, it's best to try and test and experiment and hope to be able to calibrate your model to what's best. The most sophisticated of these is probably the green ant method. So urban areas. Now this is where we are seeing direct rainfall applied quite a lot, and it is quite nice. You put your rain directly onto your model and then you have your pipe network sitting underneath that, and you got that nice combination of overland flow with your pipe network flows underneath. An interesting aspect is how you deal with buildings, and once again there's various views on how best to do this, but one of the ones I guess I like quite a lot, and it's been used in Sydney and elsewhere, is that buildings where if you like on the steeper slopes, the areas that aren't really flooding, effectively would have a very fast runoff because water would fall on the roof and shed very, very quickly. And so for those very shallow flows, you actually want a fairly low Manning's N value. For buildings which actually located within a flow path or an obstruction to flow somewhere, and that normally happens once the depth of water gets a bit higher, these buildings can be modelled as very high Manning's N to obstruct the overland flow. So what we tend to do for these buildings is you have that very low Manning's N for very shallow depths when the water starts to first hit the model, and then after that, once the water starts to become overland flow and the depths get higher, you sort of phase into much higher Manning's N values. And that is one way of, if you like, representing a building in your model in terms of the water will find it very hard to work its way through that building in those deeper depths. So that's actually quite a nice way of dealing with buildings in the direct rainfall model. So calibration and verification. This is always the hard one, because often we just have no data whatsoever. It's no different with direct rainfall models. If anything, it's probably more important because of its being new to the industry. It's really, if you can at all calibrate your model to historical events of any sort of data you can get hold of, that's very, very important. And if you like the preferred option, you do need good data, particularly for the small urban environments. It's often very, very hard to find that. If that luxury isn't available to you, you can, of course, do comparisons with traditional methods, with your RAS modelling, for example, or you can even be brave and compare with the rational methods. So when you're doing comparisons with other methods, you've really got to give each a grain of salt, and no method is going to be perfect. Once again, if you're getting similar sort of results, well, that's a good outcome. If they're getting wildly different results, you need to go and look at both models, if you like, and just see whether there's something not quite right. But it is important, particularly when you're new to this, to do these checks to compare with other methods and so forth. Another really important thing for modelling in general, once again not so specific to direct rainfall, but just modelling in general, is to sensitivity test your key parameters. It's really important as modelers that we have a feel as to, well, if we increase Manning's N by 50%, does that actually change our results very much? And sometimes we can be very surprised that what seemingly will be a very big change to your parameter has a very minor effect on your results. When you are testing different parameters, calibrating a model and so forth, you should be very tuned into how different parameters change your model results. And the only way you can do that sometimes is just to do little test runs, comparing those parameters and comparing the results. So please do that and take that approach. As I said, it is a new approach to the industry, direct rainfall modelling. So consequently, there's very limited published data on this approach. And there's no real guidance yet on what parameters to use, hence the need to be comparing with other methods or calibrating your models. But as time goes on, I think we'll see the industry become smarter and smarter on this style of modelling. And this sort of information will become more and more available, and there'll be more papers and more publications from which we can draw some knowledge from. Another fundamental one is, of course, your basic volume checks, and the XP2D will spit these out for you. And this main thing is that that you are getting convergence in your solution, and a poorly converging solution will occur if you're getting a high mass error. So the mass error is one of the key parameters to monitor. And I won't show too many equations. In fact, I think you're lucky today. This is the only one. So basically, you do need to keep an eye on that volume balance and look at what is on off. There's a few ways of looking at that, and Gavin will be able to show you some of those. Here's one, for example. This is just showing the change in mass error or the change in volume. Oh, this is just change in volume value, so that's actually not mass error there. But you can plot off things like the mass error over time and just check that this all works. If you've got the same rainfall over your whole model, it's actually quite easy to do some simple volume calcs just using Excel, just the amount of rain going in times your catchment area. And is that what comes onto your model? And is that sort of what comes out? That's what's left on the model. So it's always worthwhile doing those checks. Never trust a model can be a good motto. So a couple of images here, just giving you a bit of a feel as to between the traditional approach and the direct rainfall approach. So the image on the far left has used a hydrologic model to discretize the subcatchments, and model has been fed onto this 2D domain using the source over area type approach, and you get results that look something like that on the left there. If you use a direct rainfall, so this is exactly the same event, and you just push that rain directly onto this model, you actually get those sort of results. As you can see, the whole catchment is pretty well wet. And a lot of that dark blue you can see there is literally only millimetres deep. So it's not really flooding, it's just water on the ground, or water skimming along the ground. The far right image, is just removing all those very, very shallow depths from your mapping. So what you're looking at there is where the depth is greater than 5 or 6 centimetres. And compare the far left with the far right, you'll see that you don't get different results in your urban area down in here, for example, but you get a better definition further up the roads. You get a more realistic representation, I guess. In this very flat ground which this urban area is feeding onto, you do get quite different results. And that's because the direct rainfall has gone on to hundreds of cells in this area, where on the far left one it's just had hydrologic catchments feeding into sort of controlled areas, and so you don't have really any idea where the water is going to go or where it's going to pond, and so you do get a much better representation of the ponding patterns in that flat territory. It's also quite interesting. It's also important to compare your results in terms of simple things like time history. So the graph on the left is a flow out of the model using the more traditional approach, and it peaks around 3.5 cubic meters a second, and a little bit after 1 hour. The flow on the right is at the same location. It's peaking earlier and higher, so it's peaking around 5.5 cubic meters a second, around about half an hour earlier. So you are getting quite different responses. I mean, this is just a little test model that's been set up to demonstrate the point. But, for example, if you really believed or you had calibration data that supported the left-hand graph, well, then you would probably need to look at things like varying your Mannington roughness at very shallow depths to, just delay how that high rainfall moves through the system. But it's not to say the one on the left is right, and it's not to say the one on the right is right. You have to make those judgment calls yourselves to some extent, and that's where calibration data and some industry standards are going to be needed for this type of approach. So for those who want to read more about direct rainfall and they're not familiar with it, there's actually an excellent chapter in the AR&R Project 15 document. There's a link there on the screen that you can see where to get that from. And it's a good collection of thoughts from about a dozen or more practitioners that we all got together some years ago. It's a very good source of information on direct rainfall modelling and the types of traps you might fall into. So I'm going to hand over to Gavin now to give a live demonstration of how you set up a model and look at results and so forth.
Thanks, Bill. So as hopefully a good introduction to direct rainfall from Build Out. This is the site that those couple of screenshots from a few slides ago were taken. It's a relatively flat catchment, but I'll just turn off the results and sort of step through how this model was built. So on any typical area, and I'll just zoom in on the urban area to start with, we do have a relatively flat site, and inside our software, key processes that I would normally go through in building a model is get a good aerial photo, puts us into frame, get any 1D pipe information if you are doing an urban model. You have that ability, get GIS information or get a surveyor out there and pick up invert levels, import those into the 1D aspects of the model, and again take advantage of this 2D capability that is there, that you only have to build these very discrete one-dimensional items rather than having to define all of the overland flow paths. If you only have to deal with pipes and major structures in your model, you save time.
That's a lot easier.
You save time. You know, I think Bill made a really good comment. You can build this kind of a model in 15 minutes. It might take all night to run, but you can build these models very rapidly in this sort of 2D framework. So into the software, we've imported in some LiDAR information. And LiDAR information is generally available from either your local or state authority, depending on where you sit, either in Australia or abroad. I do know that some international countries probably lack this information, and that's a bit of a downfall in the short term. But of course, that will definitely change as the years progress in the international framework. So we can see here we've got very limited contour variation in the colours here, and the area that we're discharging into, this very flat area, it's very hard to try and identify how does this paddock drain. It's very erratic in its drainage patterns. Survey information, the surface and the 1D structures is sort of the start. Beyond that, the next pieces of information we typically go through relate to land use. And so this particular model, we've been able to build in obviously the road geometry for the area of interest. We also have built in buildings, and we've gone through the process that Bill described a moment ago, and we applied some information to this particular land use. And if we go to its data tab inside our interface, there are sort of two potential simple methods for roughness that we could apply. You could just go constant, 0.3. But for those who listen to the previous webinar on structures in 2D, you can get this mounding of water that can fall off these little polygons that are inside your network when you go with this constant method. So trying to get away from that is why we could go to this variable approach. And if I edit that curve, very simple to just apply. What we've done here is the first 100 millimeters has a relatively smooth Manning's value, and then jump it up to the 110 mil mark, so a very rapid jump there, and then ramping up to that 0.3 as depth progresses. If you thought your house was going to be completely underwater, then you may wish to consider reducing that Manning's roughness, but by that time frame, I'm sure you've got greater problems in your model. Again, you may need to also reconsider the potential other setup issues in your model relative to the depth characteristics of the shallow water equations as well. If you start having 5 meters of water on a 1 meter cell, you're probably stretching the bounds of those calculations. In terms of abstraction or loss to the software, that's another important part from a land use characteristic. Bill talked about this abstraction where we could just simply remove the water effectively from the data graph or the infiltration options. And if I click into here, I actually haven't set one up for this particular example, but I'll just call this 2D land use just to show you how this can be done on this particular layer. And if I edit that one, this is where we get to some of these key elements. And of course, if you understood the USDA soil types, then by all means you could grab those directly from within the interface. And If we're in a sandy clay environment, then those particular parameters would come across automatically for us. And then the method for either green amps or initial continuing loss methods are available. And Bill made mention too that the Horton functions will be applied to our 2015 Service Pack 1 release, is on our current schedule of development. So that's relatively simple to apply this information to these land use. I'll turn this off. I don't want a loss in my buildings in this particular model. We've got the roads, we've got the buildings. You may or may not have water bodies or other permanent variations, but another important one is shrubbery. And so shrubbery would definitely get this variation in terrain roughness. And look, the aerial photo helps define that to me, these sort of core areas. And if I turn that off, I didn't include a photo, but I have a photo of this stand of vegetation here. And that vegetation gets to about 3 meters tall, and a Sherman tank would probably not be able to drive through it. Again, a high roughness for the balance. And I can overlap these land uses and with priority to the calculation set. The higher up on our list to the left-hand side, the more dominant that land use is, and that'll be aggregated when it's passed through to the engine. So very, very useful to us. So I'm just going to minimise land use just for the moment. I'll turn all those off just to get back to the aerial photo so it's a cleaner view. This particular model is my 1D model. So this has actually got some 1D catchments that have been basically input into the software. If I just clean this up. So these yellow polygons are my local catchments. There's obviously a fair bit of work goes into trying to review the terrain and understand where the pits are and apply those catchment areas to each individual pit. And to show an example of that, if I were to just zoom in this park in the middle of the model, and I go into this particular node here, so I'm assuming this catchment is draining towards, then I'd have this, it's just under a half a hectare catchment area. You would define the characteristics for a standard hydrologic calculation set. For rafts users in the audience, much the same. So we use Lawrenson's method, which is the key method for both rafts, XP rafts product, and certainly the dominant hydrologic routing method for Australia. That would then be fed to that point. So you have no surface flow or no representation of surface flow in this park. And when I'll just turn off these catchments, we've got the idea there. Inside the interface, we can then run the model, define our time steps based on our grid. The grid in this particular model, I think we've just set it, just for this sample, at a 2.5 meter grid size. But look, I'd probably want to push that down a little bit. 2 meters might be more ideal. If you have the resolution in your underlying survey, maybe a meter might be useful as well. But every time you make that cutback or increase in resolution, you do come with a time cost in your calculations. Obviously, halve the cell size, you end up with 4 times as many cells, and then you'll change the time step. So it can take 8 times as long. So rapid changes in these models with these sort of changes. So I'll turn that grid off. And for this particular model, I will take the gamble and I'll play through the water depth animation just to sort of show how this model sees the water propagate from the model. And we're about 8 minutes into this model, and we're starting to see water at the low point, the sag of the road, and it's starting to get into the overland flow path downstream and building up. We've basically met capacity in the 1D underlying network, and we're relying on the 2-dimensional surface flow. And we're only seeing the water adjacent to these nodes. But the peak of the particular storm on this catchment was a Australian rainfall and runoff 1987 100-year 60-minute pattern, and the peak of that pattern, of course, happens around the 30 to 35-minute mark. And that's the general propagation of flow from this model. I'll pause it at that point. At the end of the day, it's all well and good to say that I've seen this animation. It's really good to show a client or a council representative or something to demonstrate you've done some really clever work and show this change of flow. But at the end of the day, most engineers are typically interested in the maximums. So we can turn those on automatically inside the software and get to this maximum of all time steps relationship. And if I zoom out, we end up with that overview that we had in the slides previously. And this is an unfiltered result set. And because fundamentally I'm not having to hide out or trim out the flows in people's backyards. I love it when we produce a direct rainfall model and they say, oh, but there's water in the backyards. My backyard floods. But as Bill said, you're generally talking about very shallow sheet flows. And when it rains in my backyard, I get water there too. We jump forward. We take this exact same model. This will just give you an indication of how long it can take to open up these data sets. So we've got a big LiDAR tile in behind this particular model. It's useful to get a feel for how long these models take to open, and bring in some CAD information as well to support our imagery. So on this particular model, same input, but all we've applied is, we've turned off those catchments and we brought in this single polygon. And on this single polygon to the software, all I have to do is right-click this polygon, edit its data, and nominate from a suite of storms what it is. So this is the location. It's the 100-year, 60-minute temporal pattern. And if I edit that, I can have a look at the hydrograph that's been applied to this polygon. So I didn't have to worry about the 75 or 80 odd sub-catchments that we had in this small area of this model. It wasn't relevant to me. I'll get back to the model, and that's it. That's the bulk of my my catchment scale rainfall based calculation done. Just quick, very, very simple. Trust me, when this model was prepared, I'm sure the engineer would have much rather jumping to a direct rainfall model rather than having to discretize all those small catchments. But nevertheless, once we've done that, we do have those same land uses in play. And this time, if I turn on the water depths, I'll just hide that orange polygon, and I hit play, same result, same site, and boom, it's blue. We on the very first minutely time step, I'm at 5 or 6 minutes in, the site goes blue. And some people, when we say, oh, if you haven't seen this before, wow, there's water everywhere. And of course there is. That's how it rains. And we're then getting to see the accumulation as these flows, using the shallow water equations, are accumulating these low points, getting down to the park area. Luckily, whilst this street floods, it does fall over into a park, and the private property is generally sound, which is a good thing for this catchment. It can be hard to look at. And so what we can do, we can run some very simple filters. I'll stop this playback, jump over to my favorite maximum result anyway. And in our software, if we just right-click on the data set, we can restrict the display range to the nominal value. I've currently applied 75 mil as a cutoff. But just to show an example, if I reduce that to, my apologies, 0.05, let's not knock off half a metre of water, 0.05 or 50 mil of water, we get to see a little bit more ponding and just some of the surface undulations, or more to the point, irregularities that exist within the LiDAR information itself. And look, it's almost as simple as that for these particular models. For this particular model, it looks pretty good. I'm not going to say that any of the buildings are at too much strife, which is a good thing. But my next sort of case study might not reveal the same. Same sort of setup. I have this other model, different site, and we've applied the same principles to this particular model. We have a 1D pipe network underneath. We've got the direct rainfall over the top, and if I turn on the water depths, I'm actually going to filter this particular. I haven't filtered this one down, it's a different site, but I'll knock off, again, 0.075, so 75 mil of water, and I'll hit play on this data set. And this data set has a bit of a valley, and a development was done in the, I will say, late 1960s, early 70s. Stormwater calculations were by no means based on the 2D shallow water equations. They would have been loosely based on the rational method probably at the time. And we can see we've got some flows. Turn off that rainfall polygon. So we can see where the road geometry is. I might turn off that surface. We can see this valley, where these buildings are. And if I just turn that surface off, we'll see that a bit better. And we'll soon start to see definitely some overland flow that unfortunately has to scoot around these buildings as the road capacity is exceeded, and it's starting to flood through these buildings. So certainly not ideal properties to go out and buy as an investment property. But that's showing that inter-catchment, that cross-catchment overflow that you might see on any standard project. Doesn't matter how good the 1D or the pipe network underneath it is, in the event of any localised failure, on this particular site, unfortunately, properties are at risk. And that, I think, is another key advantage of this type of method in seeing how those surface flows can interact within defined road geometries, but also in these overland flow paths. So very, very useful to see some of those characteristics in a model. What I didn't show on these particular models was some of the output elements. So inside our analyze menu, we have a 2D simulation summary. It's very simple to get at this information, and we can see changes in volume in the 2D, and we can get down to cumulative mass errors, and in this particular model, reasonably good errors. We don't have any 15% or 20% values. This is a very stable sort of model, so pretty handy on that front. You start seeing what would be a mass error that you would be concerned with.
You generally want to be ideally under 1%.
Yeah. I have seen some models that can drastically exceed that, but that's a good kind of.
Normally a sign there's something wrong with the input data.
Yeah, absolutely. Don't always blame the engine. The engine only deals with the data that we provided. So, and that's the case with any hydrologic package. Don't always jump to the application. It could simply be an error with the input data. Look, I think that realistically brings me towards the end of my demonstration that I wanted to sort of get through. Just a couple of quick things inside the software, but look, very quick to build inside the XP2D or XP Storm or XP Swim interface. Great calculations, useful comparison, I think. Gives people actually at times some comfort, I think, seeing how those flows can propagate. You can record movies from the software. You can do all sorts of fun things if you want to try and produce a DVD and give it to a potentially not an engineer. That's another good thing. Non-engineers sometimes struggle to interpret some of our output, and I think this really does even simplify those output and interpretation characteristics. Thank you again for joining us, and definitely thanks, Bill, for coming along, being involved with our series. And it's been quite good for us, plus our user base. Thanks again, Bill, and we look forward to seeing you, or if not seeing me, we're not seeing you at the moment, but seeing us at our next webinar, which hopefully will be another few weeks away. Thanks again. Cheers.